Next speaker is Harrison Grodin talking about amortized analysis by Coalgebra.
Very cool. Thanks, Steve. All right, so today I'm going to talk about, as Steve said, thinking about amortized analysis using Coalgebra. This is work with my advisor, Bob Harper. And of course, I have plenty of people to thank who inspired this work, as well as the funding agencies. All right, so here's the key idea that I want to talk about. In a category of algebras, I'm going to try to convince you that an amortized analysis is really just giving a coalgebra models. And if you don't know what those things are, I'll give you some background. But the goal is that I'm going to show you these two things are really fundamentally the same. So, okay, here's some background. In the original paper on amortized analysis, Tarjan talks about the goal of analyzing not just a single operation for a data structure, but a bunch of operations at the same time. So you run a bunch of operations in sequence and you think, well, I only care about the total cost of this entire sequence, not the cost of each individual operation. So you could have a large cost that gets offset by a bunch of small costs, and you think about the average over time. It's maybe a good way to think about it. So for example, if you think about buying objects, you might buy a pack of markers. You have 8 markers. Maybe they're $1 each. Really, you buy $8 worth of markers every 8 markers that you go through, but you can think of it like it's $1 per marker. So the green line here is the amortized cost, a small stair step, where you really think you're charging about $1 per marker. And you have the real cost, which is you don't charge anything, but at the end of the 8 marker cycle, you charge a lot. And then we have this difference between them, which we call the potential function, which is that smaller brown staircase at the bottom that slots in between the yellow and the green lines. So the idea is that the potential is representing how much cost you should be prepared to pay in a moment. Here's a less regular example. There's a data structure called an amortized queue that we'll talk about in a moment. And an amortized queue does some expensive operations once in a while. Again, it's a little less regular because you can choose if you want to NQ or DQ, and this is just one example of that. But you have this green line, which is the claimed cost that's somehow easier to understand once we see the specification. You have the yellow cost, which is what's actually happening. But you'll notice they continue to meet up once in a while, but there's often a big lag in the real cost versus the amortized cost. So we have this potential function, which is explaining to you the difference between these. So formally, to do this amortized analysis technique, you use this thing called a potential function using the potential method. So if you had a data structure, a capital D is the states of a data structure, and you had D and D prime as 2 states in sequence, D prime comes after D, then you might try to prove the following equation. You prove that the amortized cost of an operation is the real cost, like the honest to goodness cost that actually happens, plus the difference in potential. And again, this potential is some imagined cost that you are preparing in order to offset the large costs that come later. So it's just some function traditionally from the data structure states to the integers. To understand what the potential function is doing, you can think about the 2 cases at the bottom. So cheap operations save on potential. So if you had a real cost that was pretty small, the amortized cost is larger, and that difference in potential is positive. However, these expensive operations that happen once in a while can spend potential. So they can say, I'm going to make the potential go way down, and that offsets the fact that the real cost was big, even though you're hoping the amortized cost appears small. So what am I trying to do? I work on a project with my collaborators called CAF, which is an effectful dependent type theory, where we try to understand the cost and behavior of algorithms and data structures. So for example, you would write a program like insertion sort here in monadic form, and you would hope that you could understand the cost of insertion sort. In order to do this, we use effects. So CAF is polarized, like call by push value, the enriched effect calculus, and linear and nonlinear type theory. And we instrument programs with a primitive called charge of $C. You can think of that like printing C, and you want to count up the amount of printing, the amount of cost Cs that are printed. So an important property in these languages is that effects commute with computations. So for example, if you charged at the beginning and then had a lambda expression, you can actually push the charge into the lambda expression. Or if you had a charge before a tuple, you can push the charge into both components. So if you got the idea before that amortized analysis is about deferring costs from now until later, if you look at these equations, you might start to wonder if there's a connection. At least that's what I did. So semantically, we live in the category of cost algebras where we're using the writer monad for some cost C. Usually this is the natural numbers. And then we, of course, use the free-free full adjunction between that and the base category. Just a couple notations that'll come in handy. we have that algebra maps from f of a to x are the same as C maps from a to u of x, and we usually write that using that middle notation just for convenience and to match call with which value as well. We also sometimes split up a function a to f of b into two components. So we have delta sub $, which tells you the cost of delta, and we have delta sub circle, which tells you the behavioral result of delta. So that's the notation we'll use in a moment. Okay, so I wanted to tell you about amortized analysis in this setting. Amortized analysis is all about data structures, and a common way to think about data structures is using Coalgebra. So a quick refresher on that, and then we'll glue these ideas together. So a signature for a data structure you can understand as an endofunctor here on the category of algebras. So this signature sigma explains if you had some state type input, what the operations provided would look like. So for example, if we wanted to talk about queues based on the example we looked at, or we started looking at, we'd have sigma of x is this product where the first component is the enqueue operation. So you give it an element e, and then it gives you an updated state. That's the power. And then we also have a dequeue operation where you say, well, I'd like to dequeue something. It'll either tell you using the left injection that the queue is empty and you're out of luck, or it'll tell you that it has an element e for you, and then it co-powers that together with an updated state that you can continue using. So for example, if we wanted to implement queues, we would use a sigma coalgebra. So a coalgebra is a pair. You give an object here, a T algebra, which is D, and then you give a coalgebra morphism, here written delta, that implements the operations. So for example, if we think about queues, then you have some carrier, which might be f of list. So you just keep track of a list representing the queue in a simple implementation. And then you'd also have a transition map, which takes in a state of the queue and provides to you both operations. Here we plug in D for x in the signature. So this is a very simple implementation. So of course, when we talk about certain structures, we want to ask about what the morphisms between them would look like. So if we had two coalgebras, D delta and S sigma, then a morphism between these coalgebras is just going to be a morphism, maybe suggestively written phi between their carriers. So phi goes from D to S, which are the carriers, and it should preserve the coalgebra structure. So in other words, if we read this square out, both paths should be the same. You should be able to use delta, do whatever operations delta is providing, and then do phi afterwards. Or you could have done phi to begin with and then use sigma, and those should be the same. So the informal way to think about this is that the specification S, the coalgebra that's specifying the cost, as we'll see, is simulating the data structure D. So D is a more complicated version of S, and if we give a morphism from D to S, that explains, verifies for us that it's a matching implementation. Okay, so let's try to do some examples of coalgebra morphisms and see what happens. Say we want to talk about that bulk cost example where we charge $8 every 8 cycles. So we can give a specification coalgebra, which has a carrier f of 1, and we just charge $1 every cycle. So we say, well, sigma is a very simple coalgebra. It immediately just charges 1 and keeps the trivial state the same. Alternatively, you might have this more realistic implementation, which spends $8 every 8 cycles. So you start out by saying that we have a carrier with a finite type with 8 elements, and we, in the case you have already gone through 7 cycles, then we, on the 8th cycle, charge $8 and reset the counter in the state. Otherwise, we just increase the counter and don't charge any. So somehow we feel like maybe these are meant to match up somehow. And the way we can justify this is via a coalgebra morphism. So if we wanted to justify the connection between the implementation and the specification, we give a coalgebra morphism phi, which has to satisfy that square from before, here written using sequential composition. So, okay, we're writing maps into f of 1. Well, the carrier of f of 1 is just cost. So we could really just give a pure function from fin8 to cost, and it has to satisfy this, this equation, which is just writing the thing above, but only at the cost part, because that's all we have. And then if you stare at this and you say, wait a second, I feel like I've seen something like this before, you notice that maybe if you had a cost model being the integers, you can just kick the phi of d from the left side to the right side, subtract it from both sides. And now you have something that looks an awful lot like the amortized cost is the real cost plus the change of potential. So somehow we just looked at what a coalgebra morphism is, And the amortization condition fell right out. So, okay, you could pick 5D is D, and then it meets the previous example. Okay, so let's take a look at another example and see if this continues to work. I mentioned that there's an efficient amortized implementation of queues. The idea is that you have two lists. One is the inbox list and the other is the outbox list. And usually this queue is very easy to use. If you want to enqueue, you just toss onto the front of the inbox list. And if you want to dequeue, you just pull from the outbox list. And occasionally you run into this bad case where the outbox list is empty, the inbox list has been accumulating some data, and you just say, well, I'm going to haul all of the stuff from the inbox list over to the outbox list. So for example, if we started with the inbox being 4, 3, notice it's kind of reversed, and then the outbox is 1, 2. We can enqueue 5, and it goes on the front of the inbox. And then we can dequeue 1, we can dequeue 2, and this goes pretty well. You run into this unfortunate case that you try to dequeue, and it says, wait a second, the outbox is empty, so it has to pull the entire inbox over, the 3, 4, 5. You get to dequeue 3 because that now it's up at the front, and you leave 4, 5 in the list. And then you can proceed like you did before, enqueue 6 or whatever you do. So in theory, this should, it's a little bit more complicated than the routine cost example that we saw before, but hopefully it should still be amortized efficient since you only do this big expensive operation once in a while. So we can give a specification and an implementation just like before. We can charge $1 per enqueue and 0 per dequeue. So here on the enqueue component, which we write using co-pattern matching, we can just say charge $1 and then give back the list where as a specification level list, we just put the element on the end. And the dequeue method is similar. I didn't want to get too far into that. The implementation is not fit for slides. It's not so bad, but I didn't want to focus too much on this either. You charge 0 per enqueue because you just cons onto the front, 0 for dequeue usually, and once in a while you charge n dollars for the dequeue, where n is the length of the input list because you had to do that big reversal operation. So you might ask, can I give a Coalgebra morphism? And the answer is yes. So the Coalgebra morphism now takes in it takes in the state, which is the pair of the inbox list and the outbox list. And it does two things. First, it gives what is traditionally known in amortized analysis as the potential function. So it charges the length of the input list dollars. And that's the classical notion of potential function. But it also integrates the behavior. So we have to say how the behavior of the specification connects back to the behavior of this efficient implementation. And the way it works is, well, if you took the output list and appended the reversed input list, that would match up with what the specification was doing. So you justified that not only do the costs match up between the specification and the implementation, but they do the same thing also. And in fact, the signature can often, the cost in the signature can often depend on the behavior. So some operations take time proportional to the size of the data structure. So keeping track of the size of the data structure, among other properties, is really important for generalized proofs of correctness. So something cool that also falls out of this is you can amortize other effects. So for example, let's say you want to break away from the cost idea for a moment and think about printing. It's the same kind of effect, but you pick that the cost model is now strings, a little bit silly. You can think about amortizing string printing, and that's exactly buffering. So you can give the equation from before. Say you wanted to buffer 8 characters at a time, then the left side says, well, if you started with a buffer of hello and you tried to print world, well, the specification would just print hello world. The right side, on the other hand, would print hello WOR, which is 8 characters that get flushed from the buffer. And then you have an updated buffer of LD, which is the last couple characters that get saved for later. And in fact, both sides are equivalent because the potential function is just, you could say it's the inclusion, or you could think more that it's flushing the buffer. So both sides are the same by string concatenation associativity. So this is kind of interesting and not something that's compatible with the traditional view of amortized analysis. Something else that happens that's kind of cool is you can talk about randomized amortized analysis. So if you use the distribution monad where you have costs under each distribution location, then you can amortize randomness. So in the traditional notion of amortization, with the amortized cost and the real cost and difference in potential, it's not so clear what the new state D prime should be if you had a randomized algorithm. But if you view this, if you take this perspective, you're just working in the category of algebras for a different monad. And you can also use a different monad, the cost across the distribution, if you want expected cost. And now you can talk about the expected amortized cost, which is something that's informally understood in the literature, but is hard to pin down precisely, especially for mechanization, unless you think it this way. Also, potential functions in this generalized setting are just coalgebra morphisms, so they compose like they should. So for example, we had the fact that you could pay $8 every 8 times to mimic paying 1 cost every 1 time. You could also say 16 cost every 16 times is an imitation of 8 cost every 8 times up to amortization. And then you can compose those to say, well, you really could pay 16 cost every 16 times to meet the 1 cost every time specification. You can also compose between different signatures if you want to use the Grodin deconstruction like this. So you can say, well, if I had a signature and a coalgebra for that signature, then the amortized Qs can, for example, be implemented via a pair of stacks. So you'll have a conversion between the stacked signature and the Q signature, and then you have an amortized analysis, which happens after you convert the stacks to a Q, and then you compare those to the spec via a potential function. Okay, so we can also meet some generalizations that are common with amortized analysis from this perspective. A common generalization that's used is that you want an overestimate for your amortized cost. So you say, well, usually the amortized cost is 3, but sometimes if I'm lucky, it could be 2. It just depends on some implementation details that you don't much want to worry about. So in order to replace the equal sign with a greater than or equal to sign, we can just upgrade to bicategories because in a bicategory, programs are ordered by inequality. So instead of having a coalgebra morphism like before, now we have a colax coalgebra morphism, which just means the square doesn't commute, but it commutes colaxly. If you think that you're in poset, which is the common case, and you pick the Coff model to be the natural numbers ordered by inequality, then you get the same condition as before if you do the same development, but now you have a greater than or equal to instead of a equal to, which is pretty good. Something nice also here is if you think about the bicategory that comes out of this construction, you can talk about which amortized analyses, which potential functions are cheaper than others. So you can say, I know that my potential function is better than another one. For the bulk cost example, both phi and phi prime are valid potential functions. They're valid coalgebra morphisms, but phi is cheaper than phi prime. So it's a tighter analysis that doesn't have as much extra difference in cost. Another common thing in the literature is that you want to be able to split potential up. So for example, you have a signature that says, I want to take my data structure and split it into 2 distinct parts. So informally, you might write something like this. The specification cost is the real cost plus the sum of all of the output potentials and then minus the. So if T is commutative, the monad is commutative, which happens when your Coff model is commutative, then you can use the isomorphism between f of a tensor f of b and f of a times b to add potential. So if you do the same kind of square as before, but now you maybe work up to the equivalence between f of 1 tensor f of 1 and f of 1, where the forward direction just adds the cost, then you get exactly the condition that we had before, but made a little bit more precise and including the behavior from the signature. Also, sometimes you want to append 2 data structures. So you have 2 distinct instances of a data structure, and you want to give a method x tensor x to x. You might at first think, oh, I really would like to just curry it and make it x to x, where lolly is the internal hum, but that's not functorial, so it doesn't immediately fall into the story, but you can just upgrade to profunctors instead of functors. So now if you give an endoprofunctor from algebras to algebras, such as the following, you think that you're working in the diagonal, by the way, so x minus and x plus are usually the same object x, just with different variances, then you can give the signature x tensor x to x, and it all works out. And just like you want, it gives you the ability to sum the input potential. So now you can sum the input potential and the output potential. All right. Well, to conclude, in the category of cost algebras, a coalgebra morphism is exactly a generalized potential function that comes from amortized analysis, but it has the added benefit that it's integrating cost and behavior. So you can talk precisely about the costs that depend on behavior. It also provides a theory of composition for amortized analyses, which is a small improvement on what's traditionally viewed in amortized analysis. It also elegantly supports amortization of arbitrary effects. So here we weren't restricted to working with cost in a commutative, in the integers or something. We were able to amortize arbitrary effects, including string printing, and we're able to support randomization and mutation and whatever other effects you want. Also, this simplifies the formalization a lot. So we, in CAF, which is embedded in AGDA, want to mechanize amortized analyses. And if you do the traditional approach, which is inductively formulated in terms of a list of operations, it gets a little bit difficult. There are a lot of moving parts, but if you think in this very slick coalgebraic way, all of the details get compressed down and you are left with a really slick formulation. We were also able to add some extensions to this. So we wanted inexact amortized analyses, and we could just upgrade to bicategories for that. We wanted to split potential, well, we could use monodal products for that, and we wanted to combine potential. So we upgraded our from functors to profunctors. And that's about all I have to say. If I could take comments and questions, that'd be great. What are limits in the category of coalgebras? Limits, I think, are computed point-wise. Is that true? Oh, that's a good question. Let me think about that offline and get back to you.
So maybe
It's
you're doing analysis over it's that algorithms from those states correspond to algorithms of algorithms. And then we've got some mention here with problems. I'm just wondering whether the students have been able to speak to the bias how they affect.
Sure. So there's a nice perspective here with bialgebras. We're working with coalgebras in the category of algebras. So we're not taught, this is at a different level. The algebras are for the effect monad, not for a data structure like lists. But if you're thinking about coalgebras in the category of algebras, that's equivalent to thinking about bialgebras with a distributed law. So it's another perspective. You can write all this out in terms of general like mathematical operational semantics, and you get what is also a nice perspective on this.
So I'd like to understand your point about the theory of composition.
Sure.
So let's say the theory of relating. So we gave two examples. A framework where a constant number, a framework where a constant word. So can you relate these two by group that you mentioned distributed products? Now more can you say that one is important than the other?
So you're saying the example with amortizing printing. You're saying amortizing printing versus amortizing cost?
Yes.
I don't immediately know how to connect those. That's true. I think it's not very common that you would, is that true? I guess if you had two different monads, fundamentally they're two different monads, you could give a morphism of monads. And you would, I guess, get an analogous amortized analysis. So if you wanted to say that you took the length of a string or something and treated that as your notion of cost, I think that should work out okay. We didn't consider that in this work, but that I think should be compatible. Yeah.
It's your cost side, the final plot effect.
Can you say that again?
That's the final plot effect.
Final Coalgebra. I think it does exist. At least if you're taking your base category to be set or something.
Yeah, what's the shape of it?
I think it's just the final coalgebra computed in set. And then you just get a coalgebra structure on top of that. I think. I can check the details for that offline.
You talked about insertion sort right at the start, but never came back to it.
Yeah.
And you also talked about composing analyses, but doing two things one after the other. So do you get it right when you do something like for the, let's say, an n log n sorting algorithm first and then an n squared one, but the n squared one's actually constant length of the list time if the data is already sorted?
So we have a recent paper that was published at Popple where we considered the inductive algorithms. So that's more just an example to get us in the mindset of thinking about cost analysis. So in that work, we thought about insertion sort and merge sort and other sorting algorithms, randomized sorting. So everything composes perfectly well there. It's not part of this work, but it's something that we already feel confident we can do.
There's a question from Discord.
Oh, great.
Which is so this person saying that they do not follow what's the cumulative condition, right? What the cumulative condition was for splitting potential, and they're asking what's the intuition behind it.
Right. So the intuition is it's the same condition as before, but when you land in this f of 1 tensor f of 1, you know that f of one tensor f of one is isomorphic to f of one, and the forward direction of the isomorphism adds potential. So if you chase down the bottom, the down and then the right direction, that's the left side of the inequality. If you look at the right side, you first compute the cost from delta, and then you compute phi on both components that delta gives you back, and you add them because f of one tensor f of one is isomorphic to f of one by adding. Yeah, you need commutativity on the motor for sure. Yeah, in order to have tensors, you want commutativity of the motor. Okay. Thanks very much.
Questions?
Oh, yeah.
So you talk about the semantics of the splitting. What happens in the type theory? Because we worked with quantitative type theory, that was really good compared to like a linear type theory where things were a bit iffy because you want to keep your resource, well, to keep your values while splitting your resources, right? So maybe you could say a few words on.
Yeah, so this project was mostly about the semantics. So the type theory is still something that we are developing further.
Okay.
We expect that this is going to be based on LNL, which is, has a value like a structural level and a linear level. And we would expect that the splitting works in the same way. This kind of lines up with the traditional understanding of potential, where it would be very terrible if you could split data structure in half and throw away half. So you have to make sure that you use potential linearly. We can talk later. Okay.
A couple of slides back from here, you had you said it didn't compute, but it was co-laxly.
Yeah.
Is this the definition of a co-lax model?
Yeah,
Okay.
it is exactly. So collapse just means you have this two-cell lowercase phi that goes from the top right corner to the bottom left corner, and it's that it's that condition. So normally that has to be equal, and collax just means make it a arrow from right to left. Lax means left to right, but here you want the specification to be an upper bound, not a lower bound.
People don't have questions. Thank you.
Excellent. Thank you.